In this second part of the section, we take a look at surfaces of revolution, basically taking an arc length and rotating it about an axis. Okay, so let's look at a little picture here. Say I've got a function f of x that I'm going to take and rotate around the x-axis in between x equals a and x equals b. Okay, so what happens when I do that? I end up with a nice pretty picture that looks something like this. It's kind of like a horn or something that you would blow through. It's open, right? It's just a surface. It doesn't actually have any solid material through it, right? I'm not taking an area or a region and rotating it. I'm just taking the curve by itself, right? I'm taking a length and rotating it around the x-axis. And the way we do this is similar to what we did with volumes, where we take a piece of the area and rotate it around, and then we integrate all of those pieces to give us the total volume. Here, however, I'm going to take a piece of the surface and see what the area of that is, and then integrate to find the rest. Okay? To take this surface and actually dissect the area, I want to take and find what we call like a ds, similar to the ds from the last video, but we use capital S here. All right, I know it's a small distinction. Try not to be too confused when I write ds down twice here. One's capital S, one's lowercase s. There's my capital S. That D capital S represents the surface, the area of the surface, as a portion of the whole surface. Okay? To find that area, I need the radius here. And then what I'm going to look at then is actually the circumference. I need the radius, and that radius is actually going to be just what my function is, right? For any x value, I plug into my function, I get a y value. That's going to be the radius of the surface at any point on the curve there. And then I need this little thickness here, which is going to be the small section of arc length, right? The whole arc length is this distance here, that's little s. The small portion is d little s, right? The same as the ds that we used in the previous video. And what we're going to do is we're going to integrate over all of those little chunks of area d capital S. So the integral of d capital S is going to give us the surface, the area of the whole surface. Let's find the area of d capital S. That's going to be 2 pi times the radius times that little section of arc length. That's like a height, right? Basically, I've got kind of a cylinder here that I'm working with, and I want the area of it. It's 2 pi times the radius times that little arc length, okay? Integrate this, and I get capital S is 2 pi integral from a to b of r d little s. And again, that little s is really like that, what I used for kind of the arc length before, or the small representative piece of arc length. So in my formula, then, that is going to show up as the radical that we saw before. Integral r here is my function, f of x, and then this d little s is going to show up, like I said, as that radical 1 plus f prime of x squared dx. Okay? And that whole thing is going to be the formula for the area of my surface when I rotate that arc length around the x-axis. Again, this is particular to rotating around the x-axis and a function defined as a function of x. Right? Things will be just a little different if we rotate around a different axis or have things described as functions of y. But for the most part, I just wanted you to kind of see that construction, how things are set up here, similar to looking at volumes, but focusing on areas here and rotating an arc length around an axis. Just one example, I want to find the area of the surface S formed by revolving the graph of y equals x cubed over 3 on the interval from 0 to 1 about the x-axis. Okay, here's my formula again. So I'm just going to kind of plug and play here. There's not a lot, too intricate going on. I need f of x and f prime of x, if you notice in my formula there. So I take my derivative to get f prime, my function is y equals x cubed over 3, and I take a quick derivative and get x squared. So then my surface area is 2 pi times the integral. My bounds are given as 0 and 1. I need my function in here. That was my radius from before. My function is just x cubed over 3. And in my radical then, I need the derivative. That's my x squared. And I have to square that. This all breaks down. It simplifies just a little bit. I'm going to bring the 1/3 out front, 2 pi over 3, and simplify under the radical with 1 plus x to the 4th. Okay? A lot of these examples are kind of doctored so that they come out nice because I've got this tricky formula set up with the radical there, and in integration that can be difficult to work with. So what is nice about this is I've got the function on the outside and its derivative on the inside, and sometimes those things come nicely together so that the integration is easy. In this case, we would want to substitute 1 plus x to the 4th, so that du would be x cubed times dx. We just have a factor of 1/4 that we have to play with. So this simplifies then to pi over 6, right? When I take the antiderivative, I'll have u to the 1/2. I add 1 to the power, I get 3/2. And then I have to divide by the new power, and that's where the 2/3 comes from. Times the 1/4 comes from my substitution. I suggest you write all that substitution out in the integration. You'll see what I mean. We end up with a pi over 6 integral. Ooh, I actually skipped a step here, I think. But what we get is when we actually take the antiderivative. Oh, I'm sorry, I misspoke before. The 2/3 comes from what's out front here already. I'm going to get another 2/3 when I integrate. I got confused. I apologize. That 2/3 when I integrate, again, here is pi over 6 times 2/3, and that simplifies to pi over 9. Then I see the u to the 3/2, and replace u to be able to use my fundamental theorem of calculus. Replace u with 1 plus x to the 4th, plug in 1 and plug in 0, which all numbers crunched breaks down to pi over 9 times 2 to the 3/2 minus 1. Okay. Just a short video incorporating this kind of new old concept using surface areas. Requires the use of arc length from the last video where I rotate an arc length around an axis. Just wanted to show you one example quick, not too involved here, just some basic ideas. Thanks for watching.